Let's learn about powderbed fusion, a wide category of additive manufacturing processes whereby parts are built by scanning of a focused energy source over a bed of powder feedstock. The scanning of the energy source, which is typically fairly high power, causes the powder to fuse by sintering or melting, and therefore by the scanning of the source and the precession of layers, builds your three-dimensional part. This can be applied to polymers, metals, and other materials, so it's a very diverse set of techniques, and in the field you have many different acronyms and process names. We will refer to powderbed fusion of polymers as selective laser sintering, or SLS, and powderbed fusion of metals as selective laser melting, or SLM. A diagram of a powderbed fusion machine looks in part like a stereolithography machine, because you often have a laser mounted above the build platform where the laser beam is directed down onto the powder via fast-moving scanning mirrors. But the energy required, i.e. the laser power, and other aspects of the machine, its precision, controls, and the need for a contained atmosphere in some cases, means that machines for powderbed fusion are often much more expensive than equivalently sized stereolithography machines. As we discussed last week, Ross Householder, who lived in the western United States, is widely credited with the initial idea for powderbed fusion AM, which led him to be granted the first patent in 1979. But independent of his work, about 1986, the history of powderbed fusion continued at the University of Texas at Austin. There, a graduate student named Carl Deckard proposed a process for building parts by melting powders with an energy source to his advisor, Professor Joe Beeman. They decided to work together and they built a machine, the first one they called Betsy, which sintered polymer powder into rough form. This was recognized by the newspapers as a revolutionary development. It was really exciting. They saw the future, but the parts were really rough. Like the one shown here kind of looks like three-dimensional burnt toast. But everything starts with the first part in the first machine, and they also received a seminal patent for their idea and founded a company which was called Nova Automation. That was later named DTM, and it commercialized their selective laser sintering, or SLS technology. Here we see a picture of one of their first machines, and those were sold into the marketplace mainly for purposes of rapid prototyping. The team at UT Austin and the team that grew to follow was very creative, and many of their inventions remain commonly used in powderbed fusion AM today. These include precise temperature control of the build atmosphere, important to get high-quality parts, as well as specific mechanisms such as a counter-rotating roller to finely and uniformly spread the powder over the build platform. Now, as I said, at that time, polymer SLS machines were mainly used in rapid prototyping, but at the same time, both in the US and in other places such as Germany, there was initial R&D on powderbed fusion of metals. Particularly at the Fraunhofer Institute for Laser Technology, there was great work in developing foundational approaches to scan higher power lasers to melt metals selectively. And both in the US and in Germany, the first commercial selective laser melting printers reached the market in the early 2000s. And that technology has grown rapidly, in part because of advances across the field, materials and machines, but also because of the provenance of lower cost lasers at the powers needed to melt metals at an effective rate. As I said before, powderbed fusion can be applied to many different materials. Here we see examples of its use for polymers, for prototyping, metal components, both ferrous and non-ferrous metals, as well as cases where powderbed fusion is applied to ceramics and unique composites. Many large companies have been using SLS of polymers for prototyping for over 20 years. The example here is Dyson, the consumer goods company that makes, among other things, vacuum cleaners. And they've been prototyping the mechanical components of the vacuum housing using SLS, taking many parts and then assembling them together to make working prototypes before they commit to the tooling to scale up manufacturing. Here's a quick look at the workflow for SLM, selective laser melting. First, the machine is loaded with the build platform and the door is closed. Then the chamber is purged with inert gas, which is needed to prevent oxidation of the metal at the high temperatures of processing. The chamber is heated up to an intermediate temperature, and when that's all set, the laser starts scanning. One layer at a time, and in between layers, new powder is spread across the build surface. When the part is complete and it's sufficiently cool, the machine can be opened, and the base plate is removed with the parts attached, and then post-processing is done. And among processes, arguably SLM has the most intensive post-processing, which typically involves heat treatment to relieve residual stress in the metal part, support removal, which is difficult because the supports and the metal are the same material, and surface finishing in many cases. The base plate is often machined after the parts and supports are removed and reused in a subsequent process. To date, SLM parts, because of these complexities, have targeted mainly high-end applications. But these are still very valuable. For instance, applications in aircraft and spacecraft. We've seen GE's fuel nozzle made in part by selective laser melting and enabling a higher efficiency for combustion in the engine, as well as SpaceX, which prints large components of its rocket motors using SLM technology. Also in tooling, real production tooling, such as injection molds that have internal conformal cooling channels. Here's a miniature of an injection mold tool for plastic cup manufacturing. This comes from us from the company EOS, and you can see via this cross-section the conformal cooling channels that allow the cycle time to be reduced and the part quality to be higher. Also, SLM is being used in tooling for machining operations. Mappal, a German company, sent us these tools, this one at an early stage and this one at the finished process. And again, the reason for SLM is complex geometries for internal cooling, because by circulating cooling fluid through a spiral path along the tool, you can do higher speed machining and therefore increase the productivity of manufacturing. The really beautiful complex geometries that SLM can achieve extend to very fine lattice structures, three-dimensional structures that are impossible to make other ways. And this is used in the insides of lightweight, strong parts for various industries, and also in medical devices. And here's a half section of the acetibular cup of a hip implant made by electron beam melting, a variant of powder bed fusion, and the main reason we use this technique is because it can make this fine lattice structure on the surface that helps integrate the implant with the bone after surgery is complete. And one last example here is this large component used for an oil and gas application. It's made first by selective laser melting, so it can have this internal lattice structure and the included pathways for carrying fluid. But after the 3D printing and post-processing, a lot of CNC machining is done to give it its finished characteristics. So it's a great example of what some people call hybrid manufacturing, combining additive with conventional processing. Now, as the industry grows, quality of parts made by SLM is improving and cost is dropping. And that means we're starting to envision other, even bigger applications. In the past couple of years, the automotive industry has started to get really excited about metal 3D printing, including SLM, because they see it can realize new designs and not only enable design flexibility, but let them think about consolidating supply chains. One exciting example is this project from a consortium of companies in Europe looking at a new design for the space frame of vehicles, which combines traditional processing, specifically aluminum tubes, forming the beams in the automotive structure with junction parts made by metal 3D printing. So there again, combining existing and emerging manufacturing technology, we can envision new designs for very valuable industrial applications. As a result of this and more, the SLM industry is growing rapidly. German machine manufacturers still have the largest market share, but the industry is becoming more geographically diverse, and there's great activity really all around the world, including in the US, other European countries, and in China. And the rapid growth means there are an increasing number of machines on the market and on factory floors, and each company has typically a different process name, but they're all basically the same fundamental process of a high-power laser scanning over powder and melting metal. And this includes production systems that give higher speed than before and enable continuous operation, and the additive industry's end-to-end production system for selective laser melting fits in this category of enabling industrialization. Now, the process of selective laser melting appears straightforward. It's just scanning a laser over metal powder and causing it to melt and solidify. But you might realize that it is extremely complex. This is because of the very fast temperature changes that occur and the coupling between heat transfer and fluid dynamics of the melt pool. We'll dive into this later on in more detail, but I just want to say that we're learning a lot in this field by techniques such as high-speed imaging and sensing inside the printers and simulation of the process. And this is really becoming critical to industrialization. Some of the most complex problems in additive manufacturing can only be solved computationally and based on a lot of data. And those techniques are working with our good materials and mechanical engineering to take the technology forward. Now, powder bed fusion of polymers, typically called selective laser sintering, appears similar to powder bed fusion of metals. But it requires much lower temperature and thus lower energy, of course because polymers melt at lower temperatures than metals. In addition to heating the polymer with a laser, in SLS the polymer is typically preheated to just below its melting point, so that can further increase the rate relative to the energy you put into the process. For these reasons, SLS of polymers is a pretty high throughput process relative to other processes at the same resolution. A commercial SLS machine can build parts on the order of liters of volume per hour, which is at least 10 times faster than some extrusion and photopolymerization, aka SLA systems. Another attribute of polymer SLS is because the stresses are low, you don't need support structures. The powder bed itself provides enough support to hold the part during its formation. And while there's post-processing, for instance, removing your part from the bed of unfused powder and cleaning it off, that gives immense flexibility in the process. You don't have to worry about the cost and time of post-processing and effects of those support attachment points on part quality. There are also a couple new exciting powder bed fusion technologies for polymers that are variants on what we know about SLS. They're called high-speed sintering, a technology originally developed in the UK by academics there and now being spun out by companies including VoxelJet, and multi-jet fusion, a technology that's brought onto the market by HP, the same HP that we know for leading in 2D printing. Both of these techniques use infrared lamps instead of focused scanning lasers to fuse the polymer powder, and in order to use an infrared lamp that exposes the whole build area at once, the techniques first deposit by inkjet printing an ink onto the powder that determines where the powder absorbs that infrared light and therefore melts together. I also want to say at this junction that the use of the term sintering, as in SLS, is a bit of a misnomer because the polymer is actually melting, but the use of the word sintering has stuck in the industry, so we'll call it SLS. Now, to my assessment, these high-speed sintering processes have comparable speed to conventional SLS of polymers, but they're attractive for a few reasons. First, material recyclability is possible in these processes. The machine architecture is simpler because of the mechanisms involved, and you can also use jetting to modify the material properties, such as to impart color. And HP also introduced a multicolor printer, which was used to make this white duct component with a hollow interior and a thin wall, and this multicolor chess piece, with color finely graded from bottom to top and different on the inside versus outside. Before I conclude this introduction to powder bed fusion, I'll say that the technique is not only applied to many materials, including polymers and metals, but can also involve other methods of fusion in addition to sintering and melting. These include cases where two materials are presented in the powder bed and only one melts, but that melting is enough to pull the final material together, and also cases where chemical reactions rather than melting are used to fuse powders. We won't address these in more detail, but if you're interested, I encourage you to follow the research of Professor Jean-Pierre Cruth, who's from the University of Leuven in Belgium, and he's published extensively on all methods of powder bed fusion and been very active in the industrial space.